Hello and welcome to lesson 2 of recapping P8. Today we are looking at generating electricity, which is the second part of P8. The first one we looked at was physics on the move, and now, as I say, P8.2, powering the earth is the official title. So I'm going to briefly go through all the information you need to know. There is a fill in the gap sheet available on Google Classroom as well. Obviously that is optional, but watch, hopefully that gets through everything. So the first thing we're going to look at is renewable and non-renewable. They're basics, I'm hoping you know these already. Renewable energy sources can be replaced or regenerated. The important thing is that they will never run out. Examples include solar, geothermal, hydroelectric, and many more. Wind, wave, tidal, etc. Non-renewable energy sources will eventually run out. They can't be replaced. These include all fossil fuels and nuclear. People quite often forget nuclear from the non-renewable side. So I've listed 7 different resources here and briefly said how it works. In your notes you actually have this table, but you can see I've massively summarised what you should be seeing. So biofuels, for example, anything that has come from a living being, so wood, or you could have feces, things burnt to heat water, create steam, turns a turbine, turns a generator. Advantages: renewable, easily replaced. The plants take in carbon dioxide, so you could say that they are carbon neutral. Disadvantages: takes up land that could be used for crops, releases CO2. All fossil fuels, haven't bothered to separate them out here because they've all roughly got the same thing. Burn them in a power station, release energy, heat water, create steam, turbine, generator, etc. Advantages: quick response time. We already have the power station set up, so very quickly you can go, right, we need more power, stick some more coal in, done, power comes out. Disadvantages: we know this, release CO2, non-renewable, greenhouse gases, etc. Waves. Water moves the device up and down. Now that's quite key, because if we compare it later on to tidal water moves the device in and out, like backwards and forwards, but in waves it's up and down. That movement is connected to a generator, which makes electricity. Advantages: renewable and cheap. Disadvantages: negative impacts on wildlife habitats. So because you've got to have these machines in the water, fish and other marine animals are affected. Wind turns the turbine connected to the generator. Advantages: renewable. Disadvantages: unsightly, that's just a scientific word for ergly and noisy. Geothermal. Nuclear reactions below the Earth's surface heat water, turns the water to steam, turns the turbine, turns the generator. Advantages: renewable. Disadvantage: construction can affect the stability of land. Also not available in every country. Tidal. This is our comparison to wave. Water moves a device in and out, and that movement is connected to a generator. Advantages is renewable. Disadvantage: costly. They also, because you've got to have a whole tidal barrage, and they also, again, like waves, disrupt habitats. Hydroelectric: build a dam, water rushing through, turns a turbine, turns a generator. Advantages: renewable. Disadvantages: costly to build, and you can have to, in order to create the dam and the whole reservoir, you quite often have to flood areas, and that can again damage habitats. So that was me talking through a lot of information in a short period of time. So this is 3 different uses of different energy resources and what is currently being used. Currently we use for heating fossil fuels, biofuels, solar and geothermal. Transportation, we tend to use fossil fuels and biofuels. Generated electricity, no real surprise, all of the above. So trends in energy consumption. Sorry, I don't know why this is, let's just move that up. Okay. So the energy we consume has increased because the population of the world has increased. The use of electricity has increased. The use of transportation has increased. But there is issues with that. Eventually fossil fuels will run out and they will become more expensive and harder to access before that point. Burning fossil fuels and biofuels release CO2 into the atmosphere, leading to the greenhouse effect and climate change. So let's look a little bit more in depth at that bit. Greenhouse gases, examples of which are carbon dioxide, methane and water vapour. They absorb heat energy, infrared radiation, preventing it from escaping into space. This keeps the Earth warm enough for liquid water and living things to exist on it. So that's brilliant, that's actually very good. Greenhouse gases are not bad in themselves. but too much of them in the atmosphere leads to global warming, where the average temperature of the Earth rises quickly, which is what we're obviously seeing at the moment. So here's a lovely diagram just showing that. You've got infrared waves coming from the sun, going down to the Earth. Some of them are then reflected back off of the Earth and would normally escape through the atmosphere, but instead they are unable to escape because they are trapped by that layer of greenhouse gas. Nice and easy. So now let's look how electricity that is generated in a power station gets to our house. And this is the national grid. So on the left-hand side there, you can see a power station. I've put low-ish voltage. If you just remember the fact it's low voltage, that's brilliant. And a high current is generated. You do not need to know the number of volts that is generated in a power station. So you don't need to know that 25,000. It's just there to illustrate it. So you've got a lowish voltage, a high current. It goes up to a step-up transformer, which I'm hoping you remember from P4, where the voltage is increased and the current is decreased. And then it goes to pylons, and these pylons carry the electricity. They do it at a low current and a high voltage. The reason they do this is because if you carried the electricity at a high current, you would have a massive amount of power loss. So one of the equations you looked at in P3 was P equals I squared R. Power loss equals current squared times resistance. So you can see it's massively dependent on that current. You lower the current, you're going to lower the amount of power loss significantly. So through the pylons, then they go to a step-down transformer, so they decrease that voltage again and increase the current, which is safer for the consumer, where we get the voltage at 230 volts. There is a fill in the gaps sheet there, so if you would like to pause, you can have a little look at that if you've got to fill in the gaps on your sheet. If not, continue watching the video, nice and easy. So here is our equation. You've seen it before. Power is current times voltage. Example, a filament bulb has a potential difference of 200 volts across it and a current of 0.2 amps running through it. At what power is the filament bulb operating? P is IV, 0.2 times 200, 40 watts. Now this is useful when we look at transformers. So we briefly mentioned step up and step down transformers there, and this is where we use them. So they consist of a primary coil on the left hand side, wrapped around this soft iron core, and a secondary coil on the right hand side. The primary coil is where the electricity is inputted, and then the secondary coil is where the electricity is outputted. Now, if we assume that the power that is inputted is equal to the power that is outputted by the secondary coil, then we can use the equation we just looked at to say power in equals power out. Therefore, the voltage across the primary coil times the current through the primary coil equals the voltage across the secondary coil times the current through the secondary coil. Now, I'm actually going to pause here and do a second video in a second because I've just seen that one of my lower thighs has asked for help. So go find the second video. I'll see you in a moment.